Hello, today we are looking at different Multibrot sets. Multibrot sets are very similar to the Multibrots set. There is just a little tweak to the underlying equation. For the Multibrots set, we ask for which complex values see the absolute value of the following recursive sequence stays bounded. For a n Multibrot set, we modify the recursive equation by replacing the exponent 2 with n. Let's have a look at how the Multibrot morphs into new shapes by slowly increasing n, the value of our exponent. Wow, there were some really interesting shapes. It seems they always happen when n is a whole number. Let's have a closer look at these shapes. These shapes are really beautiful. They seem to have symmetries corresponding to n. You know what? The main bodies of these shapes look like epicycloids. Let's explore them some more. Let us start with the shape for n equals 2, the Multibrot itself. Let me outline the main shape of the Multibrot for you. This shape looks like a cardioid. Let us create a cardioid and see if it fits. To create a cardioid, let's consider two circles with equal radii. Let's call the white circle static and the blue circle rolling. You'll see why later. If we cut the white circle open and straighten it out, we can roll the blue circle along it. We can see that it takes the blue circle exactly one full rotation to get to the end of the line. This is expected, since the radii are equal, so the circumference of the blue circle equals the length of the white line. Now let's restore the white circle and roll the blue circle around it. While doing so, let us trace out the movement of the red dot. We notice that while rolling around the white circle, the blue circle did 2 full rotations instead of 1. This additional rotation is kinda hiding in plain sight. It occurs since the object the blue circle is rolling around, the white circle, itself has a full rotation boundary. In a similar manner, walking a straight line doesn't cause you to flip upside down at all, but walking along the equator at the halfway point you are flipped upside down in relation to your starting orientation. The trace of the red dot is a cardioid. To get a parametrization of this curve, let's roll around the white circle again, but this time we include arrows. We can see that the green arrow, pointing from the center of the white circle to the center of the blue circle, does 1 full rotation, while the blue arrow, pointing from the center of the blue circle to the red, does 2 full rotations. For our parametrization of the red curve, let's make some space at the right side of the screen, also let's display the radii. Since this curve is all about rotations, let's set the domain of our parametrization to the interval from 0 to 2 pi. The length of the green arrow is the sum of the 2 radii, and this arrow does 1 full rotation, so the relative position of its tip to its foot can be expressed as follows. The length of the blue arrow is the radius of the blue circle, and this arrow does 2 full rotations, so the relative position of its tip to its foot can be expressed this way. If we assume the center of the white circle to be the origin, then the red dot lies exactly at the sum of these two arrows. So we have our parametrization. Since the radii are equal, we can simplify our parametrization. Let's see if this curve really fits the main shape of the Mandelbrot set. Wow, it fits quite nicely. Now that we are done here for now, let us explore some of the other Multibrot shapes. Nice, we are back at Multibrot Hub. Let's have a closer look at the 3 Multibrot next. Once again, let me outline the main shape of this 3 Multibrot. This shape looks very much like a nephroid. I can show you how to create a nephroid and afterwards we can see if it fits this outline. Let's create 2 circles again. A white, static one and a blue, rolling one. But this time the radius of the blue circle is half the radius of the white circle. When we cut the white circle open and straighten it into a line, we can roll the blue circle along it again. We notice that this time it takes the blue circle 2 full rotations to reach the end of the line. That's because its radius and therefore also its circumference is half of that of the white circle. Let us turn the line into the white circle again, so we can roll the blue circle around the white circle. While doing so, let us once again trace the movement of the red dot. Once again, we notice that the blue circle does 1 additional full rotation, so it does 3 full rotations in total while rolling around the white circle. The trace of the red dot is called a nephroid. Let's include arrows and roll around the white circle again. We can see that the blue arrow does 3 full rotations while the green arrow does 1 full rotation. Let us create a parametrization of this curve. Let the domain be the interval from 0 to 2 pi again. The relative positions of the tips of the arrows to their feet play out similar to the ones from the Mandelbrot set. It's just that instead of 2 times, this time the blue arrow rotates 3 times as fast as the green one. From these terms, we can create the parametrization again. Considering the ratio of the radii, we can simplify this parametrization. Now let us compare this curve with the boundary of the main shape of the 3 Multibrot. Once again, I am very pleased to see that it fits so well. Let us get back to Multibrot Hub. There are several more shapes to explore. I guess the pattern seems to be rather clear now, so for the remainder of this video, I will be silent, so you can admire their beauty in stillness. But one last thing before I leave you to silence. If you liked this video, then please leave a like and consider subscribing to this channel. It really helps the channel out. In an upcoming video we will explore why these main shapes turn out to be epicycloids. I hope you enjoy the rest of the video. I will be silent now.